I will show you how to implement your own behavior in Bark. So first of all, when you have cloned Bark, you can see the folder here. We have opened it now in Visual Studio Code. And what we want to run right now is the documentation and the tutorials folder. And there's a run script which we can execute using the bazel command yet again. But as always, we first need to enter the virtual environment again. So once we've entered it, also in Visual Studio Code, you can see we entered here the venv. So now if we want to run the notebooks, we have the bazel run command and then specify the path, which is in this case docs. And then you can see the run file lies in here, and we can have a look in the build file how it's defined as run. So we go to the folder docs and we say /tutorials, and we ;: run. That should work. Let's see. So bazel runs now and checks what it has to recompile in order to run the notebooks. And as we see, as we last executed the tests, now it will take a while to compile Bark again as we use the run command. So when you develop in Bark, it's not very good to alternate between the test and the run command all the time. So now we have to wait for a bit. So after the build process has finished, the notebooks start running on our local host 888. And as you can see, you can also paste this link into any browser to get access to the Jupyter notebooks. So, okay, let's go to the behavior model notebook, which is the 6th one here. And in this one, we will outline how to develop the behavior models in detail. So first, make sure that you can import Bark, and that seems to have worked. And let me just go back to Visual Studio Code and show you where the behavior models are situated. So you go to Bark models, and then you have the 3 types of models: behavior, dynamic, execution. Right now, we want to focus on the behavior model, which determines the behavior of a vehicle or agent in Bark. So the behavior model class is an abstract class that has certain interfaces that have to be filled in order for a planner to be a valid planner in Bark. So you can see here we have the behavior model class, and it's derived from the Bark base type. And this behavior model has certain functions that need to be implemented. So each of the behavior models needs to implement a planning function that actually returns a trajectory that specifies the behavior for time horizon. And we have to implement a clone function that states how the behavior model shall be copied. And here, if you want to set an action externally, you can also set, with this function, you can set an action which is then executed in the next time step. So these models in the behavior folder, they are all written in C++. So if we go to the simplest one, so this constant acceleration model, you can see it is derived from the IDM Classic, okay, and this one is from the behavior model. And we implement here a planning function and a clone function. This you can see in the CPP, where we just say, okay, here is the trajectory, which we calculate using a constant acceleration, and we set this trajectory, we set the last action, return the trajectory. So these are all C++ models, and Bark provides a nice Python wrapping here in Python wrapper, where we can also have a quick look under models, and then we can have a look under behavior model CPP, where we can see, actually let's look into the HPP, where we can see we have a Pi behavior model that is derived from the behavior model, and that needs to have 3 functions. We need the plan function, the clone function, and we additionally could implement the action to behavior function. So due to this wrapping, we can then specify a behavior model like this in Python. So we import the behavior model from Bark core models behavior, and we create a new behavior model, which we called here derived behavior model, and we derive it actually from the behavior model I just shown you in C++. So this is of course not a valid model, as we do not have implemented anything for the plan and for the clone function. So If we want this to work, actually, we need to write a function for the plan and clone function. So here you can see a very simple implementation of the plan function. So we say how many trajectory points. Here it's 10. We get the start time of the world time, basically. We get the current ego state, that's time, x, y, theta, and v. And then we say, okay, we want to have trajectory points. We have 10 trajectory points, and we want to run these from a certain start to end time. And we just want to move with a constant velocity along the x-axis. That's what the x-pos does. We create a trajectory, which is always like time, x, y, so the Cartesian coordinates, the vehicle angle, and the velocity. We just fill in the parameters and the values, and then we set the last trajectory and we return a trajectory. So this is a plan function that is valid for bug and would make the car drive with a constant velocity. In Python, you can just say that you return the object itself as a clone function, then everything that has been in the object will be in the new object. Apart from this very easy to implement behavior model interface, Bark also provides very neat features for the development. So we have functions that say, okay, the observed world is always tailored towards the ego vehicle. So we can ask the observed world which agent is in front or behind us, which road are we on, which lane corridor are we on. So this makes it really simple to implement new novel planners and very fast and to prototype them. So also we have a wide variety of geometry functions based on the boost geometry functions. So we have a distance, translate, rotate, we have collision checks, and much more. So as this planning function is not as exciting as it could be, we could make use of some of these functions here and integrate them into our plan function. So if you make use of the functions which I've shown here, we can now say observed world dot get agent in front. So this gives us the agent in front of the ego agent, because each agent has an observed world that is tailored to the agent itself. And then we can say, okay, we have another function, get current position. That's just the Cartesian coordinates. So we have the Cartesian coordinates of the ego vehicle, and we have the Cartesian coordinates of the vehicle in front. So now we can just call one of the functions defined in Bark. Here's the distance function, which we should import also. So we can go here, it's already here imported. So we can import any of the geometry function from Bark core geometry. So we imported a distance function, so we can use it here. And then we can just say, okay, what is the distance between the ego agent and the agent in front? If it's less than 5 meters, we would like to decelerate. We just modeled that as the trajectory being a bit shorter in the end. And otherwise, we use a constant acceleration and the trajectory stays as it was. As before, we just set this trajectory again. Now the only difference is that the x-pos depends on the vehicle distance to the front vehicle. And now then we set the trajectory again, so we can use it in the next time step and then return the final trajectory. So if everything went well in this implementation, we now should be able to maintain a certain distance to the vehicle in front. Of course, this is still a very simple implementation, and Bark provides much more advanced distance model or behavior models in general. So one of the most common known ones is the intelligent driver model, where we do exactly that, but only with a more sophisticated and analytical equations that we solve numerically here. So basically, we also look for the agent in front, we look what is the distance, then we calculate the velocity, it moves along the street as well, and then we just set the trajectory, and we also return the trajectory here. So this is also a very nice benefit of Bark, that you have already a lot of these models implemented. One side note is that Bazel also lets you integrate behavior models that are not within the repository Bark itself. So if we look at the repository Bark, we can see that in the Bark simulator group that there is, for example, the planner, there is the planner MCTS, here it is, that actually implements the Monte Carlo tree search that can also be run in Bark and has shown quite neat results. And also, if we look into here, it should have a behavior model that it's implementing. So yeah, you can see here it's also derived from the behavior model. It implements the plan and the clone function, and it's the same as in Python, just in C++. Okay, this already concludes the behavior model introduction. And if you have any questions, feel free to ask them now.